think we'll go ahead and get started on our next Ivan workshop, Accelerating Insights from NMR Spectra Processing Data, Predicting Spectra and Elucidating Structures with ACD Labs software. I'll turn it over to David Rice at this time.
Okay, welcome to our next meeting. And as Eric said, we're continuing our theme of software with a set of talks from Demetrius from ACD Labs and his colleagues. And so let me turn things over to John.
Thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. And we have a bit of a milestone today. This is Ivan meeting number 60, 60. That we've come quite a ways, Dave and Dan, and well, we're going to keep on doing this for quite some time to come. Welcome everyone once again, and just a few words to kick things off before we get started. First off, I wanted to remind everyone of Ivan meeting, now traditional day before ENC. The Saturday before ENC will be live and in person, just inches away from the beaches of beautiful Asilomar. And look forward to having everyone join us out there, a day-long meeting in person, and also on Zoom, YouTube, and various media outlets of your choice. Anyways, MR Resources and Q1 Instruments, very, very happy to be sponsoring the Ivan Group and the ongoing Ivan meetings. A couple of highlights on MR Resources today. I just wanted to point out a couple of particular capabilities that they have become quite good at in nearly 40 years of operation. They have a very, very nicely equipped probe repair shop manned by some very, very good and qualified engineers. They will do literally anything and everything with any room temp probes, any cryo probes, Brooker Prodigy probes, Brooker helium temp probes. They'll do work and repairs on the probes themselves, and also the cryo platforms, compressors, and what have you. And check them out for whatever your probe repair requirements might be. Also, in the service contract department, they offer full service on all Brooker systems, new and old alike. They've got some of the best engineers and applications folks in the business, and they've been providing service to a large number of major pharma companies, major universities, and government labs for many, many years now. Please do check them out for, again, both service contracts and probe repair. Our sister company, Q1 Instruments, they've been around a little bit newer to the industry, going on 9 years at this point. And they've got a very, very good and capable lineup of 400, 500, and 600 instruments, including magnets, consoles, probes, sample changers, and so on, at a price point that is pretty substantially below the competition. So check them out as well. Enough with that. Dave, I'll turn it over to you and get things started, and also maybe let us know what is coming down the pike, please.
Right, okay. Krish is not here, so I will talk about what's coming up. And next month, continuing the theme of software, we're going to hear from Mark Dixon on how to use the Mastronova software. And then we do not have that one, we're not sure of the date. It'll be either the 22nd or the 29th. And then coming up after that, we don't have a meeting from March, but the ENC is very early in April. And as John said, we'll be meeting live in Asilomar on April 6th, the Saturday before the ENC. And this year, we have the agenda almost completely set up at this point. The theme will be benchtop NMR. And I think it's really exciting. We're going to have all 5 of the benchtop vendors present at our meeting, and they're going to be able to talk about what to do with their products. We're Also, we and they have invited users to give talks. So the day is really devoted to to what you can do with Benchtop, and I think it's going to be a great meeting. And of course, it'll have all the other parts of the meeting, we'll certainly be giving the Ivan Award, and we'll be hearing a little bit about the usual other subjects that we talk about at the Ivan meeting. So I hope everyone will who's going to Asilomar will get there early enough and attend our meeting. And of course, it will be on Zoom and YouTube, so you can certainly attend virtually. So that's pretty much we're through April, and we don't have anything set yet for May. So with that,
Dave, could I interrupt just for a second?
Okay.
If we could mention that the call for Ivan Award nominations is still active, and maybe if you could just mention that for a moment.
Of course, I'm sorry, I forgot that. We will be giving the Ivan Award, and the nominations remain open. And we've gotten actually a pretty good response this year with nominations. We're intending to make the decision late in February, and so we've set the deadline for nominations, I believe, February 23rd. That's a Friday. So anyway, if you've got someone to nominate, just simply send an email. Let me hand things over to Dimitris, and let's get started talking about software.
Hello, everybody. Thanks, everybody, for joining us. As Dave said, we will be talking about the ACD Lab software, in particular, the ways for accelerating insights from NMR spectra, processing data, predicting spectra, and elucidating structures with ACD Lab software. A few words about the company. The company started 30 years ago. We have birthday this year. You may have seen the 30 years everywhere on what we do lately. The company is headquartered in Toronto, in Canada, and we have sales and support offices in the UK, in Germany, in France, and in Asia. We have our software is used in more than 4,600 R&D sites in 93 countries around the world. And we passed another milestone recently. We are now more than 200 employees all over the world. Just some statistics, 90% of the top 50 pharma and biotech companies are using our software. 8 out of 10 of the top universities in the world have some form of our software. And more importantly, and what we are very proud of, is that more than 90% of the people who have our software choose to continue using it year after year. So that's something that makes us very proud. What are the important things for us? What matters for us? To begin with, it's science. Okay, we share your passion for science, and it drives us to help you improve research, innovate faster, and collaborate better. Technology. Okay, we are always aiming to use the latest technology in our software to support cutting-edge science. Partnership. We wouldn't have been able to do what we are doing without having partners on all possible fields and industries. And these are industry leaders, customers, and other vendors, of course. Very importantly, independence. We are a completely independent private company. We are not part of any other company. We are not a subsidiary, a wholly owned subsidiary, or department, or anything else. We are a private company, as I said, so you won't find ACD Lab shares in any of the stock exchanges around the world. And our only priority, as the slide says here, is are your long-term success and satisfaction. So we are very proud of this, and we intend to stay that way. Integrity. We hold ourselves accountable to honesty and fairness in all our interactions with business practices. We strive to always do this what's right. And more importantly, what matters a lot for us is you. We are not content until our tools create a significant impact for you. Okay, so these are, the values of ACD Labs. We have a very large portfolio of products, and they can be broadly separated in 3 categories, but they are not, let's say, equal in terms of size or offerings or whatever. So the first and the most important and most famous product line that we have is the Spectrus product line, which recently has been enhanced with the addition of Spectrus.js. So this is analytical and chemical intelligence and knowledge management software. That software that you use to analyze not only NMR spectra, but also mass spectra, chromatography, UV visible, X-ray. And we have also some software that is combining several parts of our offering together. We have the Catalyst D2D software, which is used for managing high throughput experimentation workflows. We have the Luminata software, which is for chemistry manufacturing and controls. And we have the MetaSense line for identifying metabolites on mass spectra. Now, as I said, recently we expanded in the web software. So Spectrus.js starts slowly getting all these options available on the web. So you can process your NMR spectra on the desktop application, but you can also process it on the web, and we will show you these things today. The second category of products that we have is the Percepta line, which has to do with predicting physicochemical properties and many more things. And yeah, as it says, molecular characterization and decision support. Finally, we have the third part, which is the enterprise and informatics services and AI and ML support. So we have a dedicated group of people, our professional services people, who are helping with enterprise deployments of the software and yeah, all sorts of very important, very complex things. Now, let's talk about Spectrus. We have Spectrus deployments in more than 2,800 R&D organizations. As I said in the first slide, in over 4,600 sites. What Spectrus does is it allows you to process and analyze all your analytical data and store in a single software platform. And this reduces software training and IT support burdens. Since Spectrus is instrument vendor neutral, you can choose the best instrument that you want for the job and just process everything on Spectrus without needing to retrain your users for everything. And of course, lately, yeah, Spectrus allows you to prepare analytical data for AI and ML applications. Now, Spectrus can handle formats from at least this vendor shown here, plus a few more that just couldn't fit in the slide. And you can import data from this. Spectrus can do data marshalling, that is taking the data, processing it, storing it somewhere, generating reports, putting them in a database or whatever. Of course, you can do processing and interpretation. You can store the data in a contextual format, so you don't just store a PDF, you store the whole thing. And yeah, when it's stored in the database, you can search for it, and your knowledge is not deep buried in a stack of papers. You can search for it nicely. So yeah, as I said before, we have 2 deployment options these days. You can have it on your desktop, or you can have it on the web. The desktop software is running on Windows, but on the web, you can have it on any operating system and browser and modern browser you wish. Okay. Now, beyond software, we offer services of consulting, and we have decades of experience with automation, integration, and digitalization. We are very proud of our support team. We have a group of more than 20 technical and scientific services support people all over the world in most time zones that you can imagine. So You don't need to, if you are located in I don't know, Eastern Europe or in Asia, you don't need to wait for somebody from Toronto to answer to your question. We have somebody located at your region. And we have, in the past few years, we have started our customer portal, which is a dedicated website for our customers, where they can go and find how-to movies, quick start guides, and other training resources. Okay, now, going more into what we will be talking about today. Today, we will be talking about the Spectrus NMR portfolio and the software options that we have for processing NMR. There are several of them, and if you look on this slide, they can sort of go from bottom to top. So at the very bottom, you have Spectrus processor, which allows you to do simple processing of NMR and MS and chromatography and optical. Spectrus processor comes with ChemSketch, which is another famous part of our software, which is used for drawing. And and you can also look and search our databases using Spectrus processor. The next step is Chem Analytical Workbook, which allows you now to store things in the database. The next step is NMR Workbook, which all these things now include the previous ones. Yeah, so NMR Workbook includes Chem Analytical Workbook and Spectrus processor. And NMR Workbook allows you to organize your NMR spectra in projects and use tools like NMR Sync and project management. The next step is NMR Workbook Suite, which adds tools like combined concurrent verification, unbiased verification, and it includes our predictions, our predictors, which are sort of an independent thing up until NMR Workbook Suite. So our predictors, you can predict 1D proton, carbon, and X spectra, and as well as 2D spectra, and we will see these things today. And then the next step, which includes everything, is our structure elucidator suite, which is our computer-assisted structure elucidation package, which comes with additional tools like a fragment search database, known structure identification, and it includes MS Workbook Suite if you want to process your MS spectra. We have some additional tools. We have the batch verification or automated structure verification, which allows you to quickly verify several structures. And we have tools for QNMR, and we have also, of course, the known structure ID. And now, most of these things up to maybe NMR Workbook, they are, or NMR Workbook Suite almost, are included into with Spectrus.js. So we will see how these things work seamlessly and how you can process your data in either, and you can also transfer data from the desktop software to the web software. Now, without spending much more time, let's proceed with the presentation. So let me introduce to you our presenters today. So, sorry, I need to approach and read a little bit my notes. So our first presenter is Ryan Andrews. He's an application scientist with ACD Labs for the past few months. He's joining us from Vancouver in Canada. Before joining ACD Labs, Ryan completed his PhD at the University of Toronto, where he explored the applications of new main group polycations towards small molecule activation and catalysis. So our next presenter is Carl Demans. Carl has been with the company for a few years now, and he's joining us from the Greater Toronto area. Carl obtained his PhD at the University of Toronto, studying the activation mechanisms of hydrogenation pre-catalysts using various 2D NMR techniques. Then he worked at the University of Toronto's NMR facility for 3 years as a postdoc, and he was aiding graduate students with the research goals. And then he joined us, as I said, a few years ago as an application scientist. Now, regarding myself, for those of you who don't know me, I am joining from Oxford in the UK. I was born in London in the UK. I studied in Greece. I did my PhD there in organic chemistry using NMR. Then I had a brief stint at the Military Center of Biological Research. And then I moved to Varian in Germany, in Darmstadt, where I was an application chemist for 8 years. Then in 2007, I was offered the option to move here to the UK and be the manager of the newly established NMR lab. And I have added responsibilities, not only NMR, but also we had FTMS, we had MRI, we had X-ray, and we had other analytical techniques. Now in 2010, as you probably have heard, Agilent bought Varian, and in 2014, they decided that NMR is not good for them. So at that point, I joined ACD Labs. Initially, I was an application scientist. And for the past 8 years or so, I've been the manager of the, I've been the business manager for NMR products. Now, what we will be talking about today, the agenda, it's going to be in 3 parts. The first will be by Ryan, and he will tell us how to import, process, and analyze NMR spectra using the Spectrus Platform. Then we'll go over to Carl, who's going to tell us how to predict 1D and NMR spectra and all the other neat tricks that we can do there. And then I will finish off by showing you Structure Elucidator and how you can elucidate structures that you know nothing or a little bit or most of. So without further ado, I will pass it over to Ryan.
Thank you, Dimitris, and thank you all for attending today. And basically, as Dimitris said, I'll be covering the tools within our ACD Spectrus platform for analyzing and processing your NMR spectra. Basically, I'm going to start with just a quick example of a workflow that you would go through if you have a clean NMR spectrum, and then I'll start showing more and more details that can be accomplished within our platform. So basically what you see here is our ACD Spectrus processor software, where on the left we have our data panels and we have our workspace in the middle. And all you need to do is you can drag and drop raw data files of interest into the platform to get, in this case, the NMR spectra displayed as shown here. And you also have the option to import structures into the platform. I'm just going to shrink the structure window down. And the first tool that I like to show is our automatic verification tool, this auto assignment tool, where what this will do is if you have a clean spectra as shown here, and you click on it, what the software does is it will perform peak picking, integration, multiplet analysis, and then automatic assignment of the proton atoms within your attached structure. And then it will give this match factor, which is a value between 0 to 1, where closer to 1 indicates a better match between the experimental data and the background predicted chemical shifts for each of the hydrogen atoms within your molecule. So in this case, for example, if you have a match factor of 0.96, this indicates that the experimental chemical shifts are a good match to the predicted NMR chemical shifts. And then the next step you can do within our platform is we have a reporting option, where if you click this report option, we have some pre-set up templates or customizable templates that will let you create this report where you have structure, for example, multiplet reporting. You can attach your own logo, as well as you get your experimental parameters and your spectra present. As well as we have an inset tool, where if you click this tool on the left toolbar, and you can highlight, let's say, a peak of interest, and you can zoom in on like a specific peak within your spectra that you would like to get displayed further, which can be useful if you have complicated multiplets that you would like to be displayed. But let's say at this point you're happy with the report. We then have the option to, just in one additional click, export this spectrum and this analyzed data into a PDF that you can store for later use. That's going to close the report. And additional options that we have now available. If you would like to export this data, you can also, using our file tool, you can export this data either as an ACD specific file type or other more commonly used file types such as JCamp and JSON are now available to be used for data export. Yeah, but at this point, so what I show is just a simple workflow of attaching your raw data, attaching a Spectra, running your analysis, and then reporting. Now I'm just going to give a bit more detail on each of the additional steps. And the first part is that Dimitris, in his initial presentation, he mentioned our vendor neutral compatibility with different NMR vendors. And basically here is just a more comprehensive list of each of the different file types and vendors that we are currently compatible with from our website. As well as this list is currently still expanding, and we're happy to be trying to be compatible with as many different vendors as possible. Yeah, so this does include a lot of the common examples such as Agilent, Bruker, as well as some newer benchtop NMR examples. Otherwise, just to further explain just the overall interface, what I showed here is we have our Spectra and our structure. These panels are movable and dockable, so you can customize this interface to display the specific features you would like to have displayed. But some other toolbars we have on the top toolbar, we have just overall tools for changing your view of the spectrum. For example, we have zoom tools. We have tools that will just let you can change, like you can highlight it to show how good your assignment is to the predicted chemical shifts. Also, we have grid lines that you can toggle on, which is more relevant when you're doing an overall project with 2D experiments, which I'll get to shortly. As well as you can view tables, such as here, you can have the table of spectral data, which can summarize all the data within your project. And then on the bottom, we have all the processing tools, which I'll be going over the most important tools in more detail shortly. So with that being said, I'm going to open up an overall new project, as would be done with, let's say you have a full set of proton NMR data, HMBC, HSQC, and carbon NMR data. And just as before, you're able to import these directly into our Spectrus platform and just by drag and drop the raw data. And here I drag and dropped the data into this project. And what all that does is it syncs all these spectra together, so it relates them all to the same structure, as well as you're able to sync all the data together. And it's just worth mentioning, upon import, what the software was set up to do. There's changeable settings, but we have pre-processing options such as Fourier transform, phase correction, baseline correction, etc., that have been performed on this Spectra upon import, and you can toggle these on or off depending on what is relevant for your workflow. As well as we have the tools, for example, for a transform, phase correction, baseline correction, and referencing if you would like to do manual corrections and override what was done in the automatic processing. The next step is, again, we can import structures into the software. All I have here is just drag and dropping a structure from our ACD-specific ChemSketch file extension, but we are compatible with a wide array of structural formats, including some common formats such as mol files, as well as ChemDraw files are compatible. And you can also import structures directly from our chemical structure panel. For example, we have this dictionary tool, which contains 180,000 reported structures, where you can type in a name, either systematic name, and more common names, or like a CAS number, to directly find and import a structure into the platform. As well as you can also draw structures. If you go to the ChemSketch window, here you can draw structures as well to add to the platform, including, we have been expanding more recently into the biologic space, where you can draw biologic molecules here just by, you can have it in simple form where it's just saying the different codes for the amino acids, or you can expand that structure and hit OK to then get the more extensive polypeptide chains or whatever biologic molecules you are studying. And then just in one additional click, you can hit this add structure option to then import that structure into your Spectrus processor window. But now that we have the Spectra and the structure imported into the platform, we can now go to the, I'll just show an overall processing of this overall NMR project, including, for example, right now I have this in a view where it's showing just one spectra full screen. We can also change this, and if you would like to stack your spectra and directly compare them, we have this option here, which lets you display different spectra at once on your screen. And you can change how many spectra appear on your screen just at the top. But and I'll change this in just an additional minute, just as to highlight a specific tool that Demetrius mentioned about our NMR sync. But what I'm going to do first is just follow a general workflow. I'm going to align these 2D spectra. So we have some shortcuts that are worth mentioning. If you press the Z key, you're able to zoom in, to highlight this magnifying glass to be able to zoom in on a specific peaks, as well as if you hold Control and use your scroll wheel, you can zoom in manually or zoom out manually on a specific peak. And then we can go to this alignment tool here. This tool lets you align the spectra by, if I click on the center of the cross peak in the 2D spectra and drag, we can move the peak to match the center of the peaks from the 1D spectra on the axes. And we can do the same steps with the HMBC data. I'm just going to zoom in on one peak of interest and then just make sure that it's centered well on the cross peaks or on the 1D spectra. Then the next step we can do is we could do the reference, but here it's already done. But one thing we noticed is we have a water peak in the spectrum around 1.7 ppm, and I'm just going to annotate this and show how to add a dark region, where if I click and drag over that peak, I can add a dark region here, which is a region now that will be excluded from any automatic analysis. And I can type in a label that I wish to type in. For example, in this case, it's water. So now I have this annotation over that broad peak, highlighting that it's water, and it gets grayed out, showing that it will not be analyzed further. But now I'll go over the remainder of the processing tools for this project. In general, just be showing the peak picking within the proton NMR spectrum and then the carbon spectrum. But what you'll notice is as I zoom in on the proton NMR spectrum, I have this synchronized tool on, so that way any other spectrum that are visible on the screen will get zoomed in or processed in the same regard. As well as we have a synchronized peak picking option, which here I'm going to zoom in on the peak around 1 ppm, where if I select this peak picking tool and click and drag over a peak, what this will do is it will perform multiplet analysis, peak picking, and integration on this signal of interest. And as you can see with this synchronized setting on, by peak picking the 1D spectrum in this project, the software also picks this cross peak within the 2D spectra. And then through the 2D spectra, it will also pick the corresponding peak within the carbon NMR spectrum. However, this peak here, we believe will be the CH3 group for the molecule, which if you can highlight, if you highlight the structure of the molecule, a specific atom, it will highlight where in the spectrum it believes would be a good match for that, the expected chemical shift for that compound. So you see if I highlight the CH3 group, it's highlighting right over that peak I integrated. And I can just edit this compound, edit it to integrate for 3. That's done. And then I can go over the remainder of, do the remainder of the peak picking just by clicking and dragging over the different peaks within our NMR spectrum. And after this, we can go check our 2D spectra. And as we see within the HSQC, all the corresponding cross peaks that matched with those proton signals have now been picked, as well as the carbon signals that would also be correlating at those same 2D peaks. So as you see, there's still some HMBC signals still unpicked. One that we can manually pick ourselves here that would be at a cross peak. And then there's the other 3 related to quaternary carbons that we can now pick directly from the carbon spectrum. And as you see, picking the carbon spectrum also will pick those peaks through the HMBC. And now let's say that we are happy with this overall analysis. We can use that auto assignment tool again. This will be used to then verify that the structure matches all the data within this project. And as I click on this, we get a match factor of 0.94, which suggests that the data matches quite well for this structure through the experimental data in the project. And then let's say you have this NMR workbook program and you would like to build a database. So when you're making subsequent structures, you can quickly run a search against your database to make sure that you either have made something you had made in the past, or if like an impurity is present that you would like to determine, you can see if it's present in your spectrum through the database. You can use this update database option here, which will then append all this data into our Spectrus DB program, which is our database overall storage program. And as you see here, it imports it into this database, and you can scroll through all the different spectra that have been appended to that structure. And as well as, I'm not going to go through it again, but you can report or export this data to use in to store on your computer, or to or to be able to reanalyze again later. So the next tools that I'll show are some of the more advanced assignment tools that our software has. So if I were to just close the open project, what I'll show next is, as mentioned by Demetrius, we have our concurrent verification tool, which what this does is it will take an imported structure and process NMR data, and then it will provide different isomers and compare those isomers to see how well both the starting compound and its isomers match the experimental NMR data. So what I have imported here is just this project that has this appended structure that's proposed, as well as a fully peak picked and multiplet analyzed proton NMR and HSQC spectrum. And what we can do is, if we go into the auto assignment options here at the bottom, what I'm going to the setting that we are interested in here is the CCV, or our concurrent verification. If I toggle it on, what this will now suggest the software to do is have it suggest different isomers that may be relevant for the structure, or that may better match the data compared to the structure that we imported. So if I hit run assignment, what this does is that here I had it set to generate 5 isomers, and it generated 5 different isomers and compares them by the match factor to see how well it matches the data. So here at the top, we had our original structure, which gave a match factor of 0.71, which is only okay. But we see here the structure, fourth structure on the list gave a match factor of 0.83, which suggests it's a better match of the data, as well as the program highlights the changes in connectivity from this structure to the initial structure, which is basically a swapping of the positions of the carbonyl and the CS groups in the molecule. But let's say we want to further verify which of these isomers may be the more relevant isomer for this project. Just going to just narrow down these windows. We can import, let's say, I'm just going to add a carbon NMR spectrum into the project and rerun that auto assignment. And now with this added data, we find that this new isomer is a better match for the data than our proposed isomer. And one similar tool we have is our unbiased verification, which is a related tool, and it's really also related to the structure elucidator that Dimitris will be talking about shortly. But what this tool does is it considers all isomers for an imported structure, basically an imported formula, and will go through all the isomers and suggest what will be the best overall structure that matches the data. And this tool basically requires a proton, an HMBC, and an HSQC as a minimum. So what I've imported here is a fully peak-pick project, including proton NMR data, COSY data, HMBC data, as well as HSQC data. And I'm going to turn off the concurrent verification just because we don't want those both running at the same time. And basically what I'll do is I'll run our unbiased verification, where now we can, if we were to so choose, we can highlight, let's say, a specific fragment that we know 100% from the data will be involved within the final structure, and hit OK. We'll get a message saying how easy the generation will be, which is basically an indication of the speed of this generation. Hit OK, and now the software will predict series of different isomers that match the data, and then suggest which isomer will give the best overall result. And just in a few seconds, now it's finished. We got 20 unique structures added to this list, which I'll expand out. And in this case, it's suggesting that this structure is an overall the best match and significantly better than the initial structure we had imported into the program. And then finally, within our NMR workbook, we also have tools for handling of stack spectra, as well as for quantitative NMR. And in terms of stack spectra, I'm just going to show just a simple example for some kinetics analysis. So here we have an overall stacked spectra. This can be generated by importing each of the initial proton NMR spectra into the program. Having them selected, and in your series, you can hit this collect spectra option to generate what I've shown here. And then the next step would be to use this group treatment tool. This group treatment tool will let you any processing you do on one of the spectra in your series, it will do the exact same processing through the rest of the spectra. I'll zoom in on the peaks of interest, and then I'll do this align series tool here. This will align a peak of your choosing to make sure that all the peaks are aligned across your entire project. And then we have this brush tool, and this brush tool is what we use to do the processing on the series spectra, where if you were to hold, click, and drag across the spectra, it will now integrate the peaks within that region. And when I release here, we get this overall plot of basically the different time points on the bottom and the heights of the peak, or the integration of the peak on the top or on the y-axis. We can create a reference signal. This will help to normalize all the signals against a reference within the spectra. So I click that reference tool, and now in this case, I'm going to use this peak at around 1.55 ppm as a reference. I'll drag across it. And now if I go back to the graph, now it's been normalized to that, all the peaks have been normalized to that reference peak. And we can do some calculations. Here's the list of the calculations we have. In this case, it's a first order kinetics, but we can also process second order kinetics, Dozy experiments, pKa experiments, and T1 relaxation determination. So if I click the first order kinetics, we get an optimized curve matching the data, that's basically calibration curve for the data, as well as it provides the K1 value, your rate constant for that project. So basically that's our way of handling series spectra and kinetics data. If I close this, I'll also show you an example. The final thing I'll show in this program is our QNMR, our quantitative NMR data, where in this case, I'm going to start with this caffeine example, where I imported this peak pick spectrum for caffeine that has an internal standard. And what we have here is you're able to do a weighted purity calculation really quickly within this project. So I can choose this strength calculation option. And what it will do is here you get this pop-up window that lets you choose your standard of interest and the formula for your parent structure that you're wanting to get the purity of. You can hit OK. And then you get basically a series, you get this pop-up window here, which will give you, where you can input the weight of your standards, your weight of the sample that you used in prepping the sample, as well as then you get the integrations for each of the assigned signals and the reference. And the software will use all this data to calculate an overall NMR strength, or basically NMR weighted purity for that sample. And you can just hit report to generate that report and proceed further. So basically you would get this report that has your structure and your weighted purity percentage. Sounds good. And finally, what I'll show is some of these tools are also being adapted more and more into our Spectrus Processor JS platform, which is our web-based platform, which I'm going to log into now. And basically, what you can do is within the Processor JS window, you're able to create a new data set, and you can either upload files directly from your computer, or you can set a local or remote directory that you can import data directly into, and the Processor JS will be able to sweep and collect that data. But all I'm going to do here is I'm going to open, in this case, again, a simple proton NMR example. If I hit open, here we have this customizable window where you have structure. You can have your different tables, your spectra displayed here, all with similar features as in our desktop program. And just like with the Spectrus program, we can use this assignment tool. If you click on this, if you have a clean spectrum, you can very quickly get, you can very quickly do the peak picking, integration, multiplet analysis, and assignment for the structure. In this case, again, you can get a match factor. In this case, it's shown here, a match factor of around 0.95, which again suggests that there's a good match between the imported structure, the experimental data, and the predicted spectra for that structure. And then after this point, you can either download the data directly using this tool here, which exports it into a .spectrus file, which is our file that's compatible, and our ACD specific file, which you can then use to either have someone else import it into their JS platform, or you can use it to import it into your own desktop platform. And alternatively, we do have a setup reporting tool here, which if you click on this, it creates a PDF exportable report in just a few seconds. And then you can save this as a PDF, etc., and use it to store your process data in your servers. Finally, if you would like, you can also create a new data set just using this upload option here. In this case, I'll go 2 examples, and I'll pick this flowdipine example because it has proton, carbon, and HSQC data. Initially, I'm going to import just proton, HSQC, and a structure. And the reason I'm going to do it this way is just showing that you can import more structure into a project at a later point. You don't have to have all the structure initially in the browser to be able to process it. So what I can do is I can go back to the upload data, go to the examples, and now add the carbon spectrum onto this project. And now that adds the carbon spectrum. Yeah, and then otherwise the tools are similar as in our desktop window, including you have shortcuts using Z or holding control and using scroll wheel to zoom in on different peaks. And what I'm just going to do is just a very abbreviated workflow where I'm able to first align the 2D spectrum. And then you can go through and do the peak picking as well as shown in the desktop platform. And this will undergo will follow the same steps. With one difference here is you can change the integral values directly from the integral tables. So I'm setting this CH3 group to be set to 3 protons. I'll zoom in on some of the other peaks. So these 2 singlets as well to 3 ppm. And I'll just go through the rest of the spectrum and integrate each of the necessary peaks. Actually, before I go further, I realized I didn't do the solvent referencing, which I'll do at this point. And then pick the remainder of the peaks in the proton spectrum. Yeah, and just like in our desktop platform, you can go back through the other spectra, and you see that it, with our NMR sync tool, it picked the corresponding cross peaks in the 2D spectrum and then through to the carbon NMR spectrum. And then the last thing I'm going to do here is just finally pick the carbon. But first I'm just going to manually change the dark regions around the DMSO signal, which you can do just in the manual referencing. And basically all I'm going to do here Just going to zoom in further. Just drag it over the whole DMSO peak so nothing gets picked underneath it. And we have the ability to pick by level to pick the remainder of the carbon signals above that threshold. And then we could do automatic assignment. And in this case, the automatic assignment then will help provide, for example, the match factor, as well as assign the different elements within this project to the various peaks. And then you can report as well as you had done before. So that is basically the extent of what I had been hoping to show today. I can pass things back to Carl and Dimitris at this time.
Yeah, thanks, Ryan. I appreciate that. Demetrius, do you have anything to say before I continue?
Thanks, Ryan. No, I don't have anything to add. I just want to point out to everybody that, yeah, as Ryan very nicely showed, we have the tools that work either on the desktop or on the web. And they are completely equivalent. You can do the same things and get the same results. And the web tools obviously offer the advantage that you don't need to install a very heavy client on your laptop, on your computer. You don't need to have a very powerful computer with lots of RAM and lots of disk space and all these things and powerful CPUs. In theory, you could even use, your phone or your tablet to process Spectra, and you can actually try to do it. The problem that we have seen though is that it's not that easy to pick the peaks with your thick finger. It's better to have an actual pointer, a mouse. So yeah, no, nothing else. I don't believe. Are there any questions at this point? I don't see anything in the chat box. Okay, I see Charles wants to ask a question. Charles, go ahead and unmute yourself and ask the question. I don't know, Charles, can you hear us? Oh, and Tamara also. I don't know. Eric, can they unmute themselves? Oh, Tamara, go ahead.
Hi.
Hello.
Thank you. This is a really great presentation. Thank you so much. And I guess a general question is, I am trying to take notes, but obviously it's not as good as seeing you walk through the processor. Would the recording be available for attendees later, just so that I can attempt to repeat what you're doing? Thank you.
So yes, the Ivan people are recording this meeting, and I believe that it's going to be placed in the YouTube channel of Ivan. And I'm not sure of the timeline, whether it will be tomorrow or I don't know, in 2 weeks or in 1 month. I don't know if Eric or Dan or Dave, you can make any comment on this. How much later does the recording appear?
It usually takes Eric a couple days to get it up on YouTube.
Okay.
Being a Thursday usually goes up on Mondays.
Thank you so much.
Okay, thank you. I see, Charles, you still have your hand raised. You want to ask a question, or should we proceed to Carl? Okay, I don't see.
Yeah, he's in the chat and he said yes. He wants to ask a question.
Okay, go ahead. Okay, he says that he wants to ask the question, but his microphone is off. You can type it on the chat. In the meanwhile, I see we have another question. What match factor value is acceptable? I think I will answer this. So obviously, if you get a match factor of 0.99 or 1, then that's definitely great. If you get a match factor of 0.1 or 0.2, that's not great. If you get something in between, then there are, you are touching something almost on religion. So some people believe that you need to have a match factor above 0.9. Some people believe you need to have a match factor above 0.8. what we have seen is that usually if you have a match factor above 0.75, this is fairly safe. In order to increase the reliability of the match factor, not the match factor itself necessarily, the best way to do it is to include additional spectra, as Ryan showed very nicely. Just adding a carbon spectrum in that example completely, eliminated all the other potential candidates. So adding more spectra will not necessarily increase your match factor, but it will make it more reliable. Moreover, you shouldn't be only relying on the match factor itself. You should be also looking at all the other parameters that are calculated that were briefly shown. So to begin with, we calculate the DP4 score, and this can help differentiate between things. But then you can also see other parameters like standard deviation between predicted and experimental spectra. You can see the maximum deviation. You can see also the integral deviations and all these things. Now, another important thing is if you have 2D spectra like COSY or HMBC, what the software does, it will look whether the correlations observed there are compatible with the proposed structures, and it can quickly eliminate other candidates. So yeah, I can't say, that anything above, 0.8 match factor is good, anything below is bad. But yeah, there are ways of increasing the reliability of this score. Okay, I hope this answered the question. Okay, thank you. Yeah, so I see in the chat box, the question was, I noticed that the baseline on the C13 NMR had a wave. How would you correct? Okay, so obviously this wave was there because of the way the spectrum was recorded. Maybe there is a little bit of background in the probe, or maybe something was not optimized for the acquisition. It can be corrected. We have several tools for baseline correction. So you can do other simple things like polynomial baseline correction, or feed averaging baseline correction, or sorts of other things. It can be corrected. We can show you if you want. We can send you a message offline and show you how to do this. It's very easy. In essence, you just click the button baseline correction and it's done. Okay, I don't see any other questions. And in the interest of time, I think we should proceed with Carl. Carl, it's all yours.
All right, thanks, Dimitris. Yeah, so I'll take over from here and talk mainly about NMR predictors. I'll focus mostly on Spectrus Processor JS, or through the browser, and then I'll swap over to the desktop software to show you a few more spectra that we can calculate. I'll also cover creating a user database. So when we predict an NMR spectrum, we use our internal database to calculate chemical shifts. But if you're dealing with a chemical space that's not well represented by our database, you can create your own user databases, make some assignments, add structures there, and then apply that when you're predicting spectra in the future. So you can kind of create a nice chemical space around your query structures in that way. And then the final thing I'll just quickly demonstrate is a batch automatic structure verification. So it's similar to what Ryan showed, that calculation of that match factor, but doing it in a batch way. Here's a folder. It has 10, 20, 100 data sets in it. Each one has a structure. Let me know which structures are close and match the data set. So I'll cover all that. But to begin, we'll start simple as we do. And right now in the browser software, I have a proton experimental data set. And then I have the corresponding structure for catechin. So the first workflow I want to cover is I'm going to predict a proton NMR, and then I'm going to compare it with the experimental data set. So in the structure window on the right-hand side, there's a little calculator button. We can calculate chemical shifts, various 1D, 2D NMR spectra. I'm going to go to 1D proton. We'll just click that. So this will send a signal over to the server to predict our proton NMR, and it comes back with a new tab down below. So I'll click on that. What we can see is proton spectrum with all the coupling. If I hover over a particular multiplet in the spectrum on the right-hand side, you'll notice that CH, or the proton there, number 13, is highlighted to show you that that's what this chemical shift represents. And similarly, we can hop on over to the structure, hover over different portions, and it'll highlight in red the chemical structure that's associated to that. But I wanted to do a comparison methodology. So there's a tiled mode, similar to what you saw before. It's activated in the top left under these layouts. I'll go to horizontal tiles, and I'm defining to look at two data sets. So I have my experimental proton up at the top that doesn't have any assignments made. I have my predicted proton spectrum just down below. I can zoom using the tools just up here. We'll focus in on this region here. There we go. And so from the prediction down on the bottom, if I hover my mouse over the multiplet, I can see that's the CH there, the stereochemistry. And then I'm looking for, a similar correlation on the top. So it could be, one of these two. If I'm looking for this triplet here, get a triplet of doublets, I can see there's a similar peak here as a triplet of triplets. So then I could use this information to assign peaks in the experimental data set above. So to do that, we have a series of tools on the left. One of them is this assignment. I'm just clicking on the arrow to change the settings. There is automatic assignment. That'll be just like the match factor calculation, assign each of these peaks to the structures. We can do it in a manual sense, which I have activated here. And so with that, I'll click on triplet of triplets. Let me activate the button first. Click on triplet of triplets, follows my mouse cursor. It's even showing me on the structure what makes the most sense based on the predictions sort of happening in the background. It's highlighting this one in green, so I'd be more confident to assign this here. And then when I click, you'll notice the chemical shift now has a 5 denoted for the atom label, and it has coloration saying that the assignment is nice. Conversely, if I forced this assignment, to an aromatic proton, we get a red coloration. So the software does interact when you're making assignments to give you some sort of coloration based on how well it matches the predicted spectrum to help you with your elucidations here. So we could repeat this process for all the peaks that we see down below, as we hover and see the suggestions on the structure, go to the experimental data set up top and click and drag to assign. I'm going to swap back to full screen mode. We have here, we'll click on our catechin data set. So there are other modes that you can look into. There's a direct overlay in the top right. If I click on that, you can define which data sets you want to overlay. And then you can define how you want to view this. So it's quite similar in terms of stack spectra. You can synchronize the zoom using the synchronize zoom button, and then see it in more detail without the structure, say, on the side, taking up the screen space. I'll swap back to the actual data set, which is, leave this dashboard button here, and we'll move on with predicting other spectra. So in this calculate button, I didn't cover any of these other options. We'll first look at the calculation method. So I break these down into 3 groups. We have a neural network, tabular, incremental, then these 3 are all related. So the neural network is basically we take our database, we create an algorithm on the back end that will calculate based on your structure inputs. You don't get really any extra information on how or why chemical shifts were calculated, but it's a very fast algorithm and its accuracy is really good. This tabular incremental works in a way that you would maybe do by hand as an undergrad. We take a chemical entity, maybe a CH2, we look at what's close by, and we add little deltas based on changes in the chemical shift. So that would be an incremental way. It's not so great with stereochemistry, or at least diastereotopic protons. And then we have a average experimental weighted or corrected weighted average. And so we call this Hose codes. It's a hierarchical ordered spherical based on the environment. Essentially, for every single proton that we're looking at in this case, it's going to look at its chemical environment. So it's going to say, oh, there's a carbon adjacent to it. There's a carbon adjacent to it. It's a part of an aromatic ring. It's going to see how far it can expand outward and match those structures within a database. And then basically the more similar a structure is in the database and its known chemical shifts, the more weighting it has when it's predicting a data set. So I like to use this one. It takes a bit more time, but I find I have more control over all the parameters. And so with that, we can look at carbon NMRs, standard, apt depths, a few different X nuclei, and then we have 2D spectra. So I'll choose a HSQC depth. It'll request calculating of the spectrum and it'll open a new tab just down below. I can click on that and load it. I'm going to fix up the axes here just to show any negative correlations, and we'll zoom out. And so we can see an HSQC here where there's distinction between the diastereotopic protons. In a similar manner, we can calculate HMBC all on the browser. And we'll open that up and take a look. And of course, there's a lot more correlations involved as this molecule is getting larger and larger. If you hover over a particular peak, it'll highlight the actual interaction on the molecule itself. So these are just some of the few options for calculating, simple 1D and then some of your more basic 2D. We do have more examples on the desktop that I'll show, but for now I wanted to show a calculation of a carbon spectrum using 2 different ways of drawing a polymer, and then we'll look at a peptide as well. So I'm just going to clean this space up, Xing out a few of these tabs down at the bottom. And then I'm going to bring in some other structures that I have on my local drive. So I'll drag in 2 different polymers, choose to upload both of them, and it adds new arrows down to the structure. And so you can see here, I don't have any experimental spectrum. You don't need one. You just need a structure to perform these calculations. But I did have 2 different ways of drawing polymers. So we can do this in our ChemSketch application. But essentially I have, N groups and brackets denoting repeating units. And then I have a fully drawn out structure. I think N equals about 4 or 5. And so if we predict a carbon in this case with the kind of collapsed structure, I'll just do a standard carbon. What we end up with in the predicted spectrum is broader peaks. So we have some fairly broad peaks, here up at the top, broad peaks in the aromatic region. And then we get some overlap. Essentially, it's sort of looking at these like expanded and then collapsing all of their calculated in between, like in the N values from 1 to 7 or so on. And it's producing a broader spectrum. If we go to the fully drawn out structure and we calculate a carbon, it'll perform a similar task, but now it's going to calculate the carbon all along these chains, and you'll end up with sharper peaks and more peaks in these ranges. Just to show it off in better detail, I'll go back to the horizontal tiles. We can zoom here. There we go. Drag that one up. We can see some differences here So I zoom in along the x-axis or drag it. All right, so we have our drawn with brackets up at the top, a lot broader peaks, and then we have something that's more applicable for showing end groups. So normally when I'm predicting NMR spectra, I kind of use like a mix of this. I'll use the bracket notation for most of the subset, but then I'll draw out a few extra repeating units just so I can see those end groups being calculated, which might be more representative of your samples. So that was polymer, 2 different ways to draw it, and a carbon NMR. I have a peptide chain as well, so I'll just drag that in. We'll upload it. I'll navigate over to it through the structure. You can see this is the peptide that I've had that Ryan showed a little earlier when you can collapse and expand the structure. In this case, we do have nitrogen 15 calculation. So I can click on that very quickly. Let me swap back to full screen mode. We can see the different nitrogen centers and where they end up. A lot more overlap in the middle here. So that's everything I wanted to show with the calculation protocol, at least through Spectrus Processor JS. So I'm going to swap to the desktop for now. Let me open that up. So this is our drawing software that interacts with the processor tool. There's a calculate button down at the bottom that can calculate Spectra as well. And there's a few more options currently. One that I like to point out is pure shift NMR. So you don't get that proton-proton coupling. You just get singlets for each of your protons, can help with elucidation. And we also have a spot here for more 2D NMR spectra. So I can click on that. Variety of different options, inadequates. The main one I wanted to show off is an HSQC Toxi. So let me click on that. And there's actually a few different ways we can calculate this. So I'll keep it as the first option. We'll click OK. So one way this predicted spectrum can help is you might have a lot of overlap between your protons just along the F2 axis. But if we're calculating an HSQC Toxi, you get a bit more, say, resolution along the F1 axis to determine which CH2 groups might belong where. And so I'm looking at this region. Sure, it's not completely overlapped, completely convoluted, but we have been able to calculate which spin system exists where. So from our structure here, we have a spin system sort of on the left here, atoms 8 and 7, and we have a different spin system 3 to 6. I can see from this spectrum by just looking at these boxes that we have one spin system represented here from the left-hand side, and then we have the secondary spin system here as we move along this chain hopping. It can help with areas of convolution. If I just zoom in here, we can see that this peak belongs to 7-8 correlation. And then this peak just very close in the proton or the F2 belongs to the other side. We can change a bunch of options for the spectra calculation parameters. Just quickly open it here. For 2D NMR, we can change the megahertz, spectrum size, whether you want more resolution, and then a variety of different line broadenings and ways to determine what calculation method you want or whether to use training databases or your user databases. So there's a lot of options that I'm not really covering today. Nitrogen, you can change the reference compound if it's relevant. And then there's similar options for 1D NMR. So that's more of the prediction tools that I wanted to cover. I'll just spend 1 minute to create a user database and add an example to it. So the first thing I want to do is create an NMR prediction database. So I go to ACD Labs up at the top. There's something called C+H predictors. I'll click on that and it'll open up the software for us. What we're going to do is jump over to the database down at the bottom. I'm selecting to create a user database. I'll go database new. And I'll just store it on my desktop for ease. User database. And I'm gonna not password protect it. So now I have an empty database here ready to add information to it. So I want to go to processor. I'm gonna load up an experimental data set. Say the same one we worked online. So here's catechin. I'll drag in the structure. Here we go. And for the sake of showing that the user database works, I'm going to purposely make bad correlations to show you how that affects the calculated spectrum. So I'm going to peak pick just down at the bottom. I'm going to use this assignment tool in the interpret section. I'm going to grab this and I'm going to force it to the CH on the aromatic ring. Obviously the software doesn't like that, and it's highlighting it in red. I'll do it one more time. And then from the database window up at the top, there's update the carbon proton database. I'll just click OK to accept the assignments that I've made and add it to this database. So now I can see in the database the 2 assignments that I've made, where they are on the structure. And now I can use this in our calculations. So I'm going to move back to processor. I'm going to go to the structure window, this calculate button. I'm going to calculate a proton. This one doesn't use the user database, so it should come in quite clean. But under the options, Spectra calculation parameters, I can define a user database down below, use the training database. Just going to add the one that I created on the desktop, user database NMR. And I just make sure it's enabled. So now we're going to use this database for calculations. Going to go to the tool and recalculate the proton. And then I'm going to go to tiled mode to see the comparison here. So you'll see calculated up at the top. This is not using our user database. It's different than the one using the database down below. And not surprisingly, using our bad database information, if I hover over this aromatic peak, it now suggests that proton would be at 2.63. So you can create user databases, you can alter their information and use that in calculations to get a meaningful effect when you're working on a chemical space that isn't naturally covered by our internal database. The last thing I wanted to show is a batch ASV tool. So I'm going to close all these Spectra. And I'm going to use batch ASV script up at the top left. I won't go through all the information because there's a lot of information. You can choose how you want to process data exactly and what we're looking for. For the sake of argument, I'm saying, hey, look in folders that I'm recommending, pull out their proton, pull out their HSQC, pull out a structure that's within the data set, and then calculate a match factor. And then I'm saying, output it to this folder and create a database to store the information. I've defined the folder or the input folder to be this one here. So I have 3 different data sets, in this case Brooker. They contain 1 or more structures and then a proton and an HSQC. I'm going to go to our output folder. You'll notice it's empty here. So to trigger batch ASV, I'll click process all data sets. It detects there's 3 in that input folder. I'll click OK. And then it's going to start churning through those. So it loads the proton, loads the HSQC, loads the proposed structure, automatically processes, calculates this match factor. In the input folders, you can actually put 1 or more structures, however you want. It'll find the best match and present that at the end in the database. Last thing I'll mention is this is triggered, through a button. We have technology that sets up an automation server that's constantly sweeping or scanning a folder. So as new data gets put into that folder, it automatically does all of this. So while that was processing, it created a database. It's going to open up my database software here. And in just a moment, it'll show us the results of the 3 data sets. It'll show it via color coordination. So a good structure matches in green, bad structure matches in red. So the 3 data sets are represented in the bottom right-hand corner. If I click on the first one, it says this is our proposed structure from our input. This is our HSQC and our proton, and the match factor was calculated at 0.93. I could go to the 3rd data set here. Take a moment to load the structures, but it'll have the HSQC and the proton as well. And we can see from the structure that we've inputted and shown in the top left, the match factor was 0. So this is not a good match. That's everything that I had to show today, at least with NMR predictors. So unless there are any questions, I'll pass this back to Dimitris.
Thanks, Carl. I see we have one question on the chat. I don't know, John, Ralph, if you want to unmute yourself and ask the question directly, or should we read it? Okay, I'm going to read it. If you have data for a lot of compounds in different NMR solvents, can the solvent-specific info be utilized for predicting relevant to that solvent?
Yeah, I can handle that. Yeah, sure. The answer is yes. There's definitely solvent effects in a proton. In the options here, I have it toggled off, but you can choose to use the solvent for the experimental data set. So if it's detected in DMSO, it'll calculate only based on information in the database that was run in DMSO. You can also choose which solvents you want to calculate for. I just said anything, but I could choose to only do it in DMSO and maybe like water if I think that's relevant for my calculation.
Okay, we have another question. Could the predictor work with mixture of molecules?
It does. Yeah, if you draw 2 different molecules and predict a proton or other spectra, it'll ask what molar ratio they're in. And so you can denote one molecule as 10 moles and then the second molecule is 1 mole. It basically calculates both separately and then superimposes them into one spectrum. So yeah, mixtures are good too.
Yeah, and you can, another question that we are asked is up to how many molecules can you have together? I have tried that with, I think, 20 or 30. Didn't seem to have any problem. Just takes a little bit longer, but in the end, you get the result. Okay. So we have another question. Can the software predict the unknown structure from its NMR spectra? Please stay tuned for this. That's what I will be showing you now.
Definitely. Thanks, Dimitris. And thanks everyone for listening.
Any other questions? Doesn't look like. In the interest of time, yeah, no other questions. So in the interest of time, I'm going to start with my part. So I will be talking to you about our Structure Elucidator software, which is our top-of-the-line NMR program, as I mentioned already, and it's doing what is known broadly as CASE, or computer-assisted structure elucidation. We've been developing Structure Elucidator for more than 25 years now, and there have been, hundreds, if not thousands, of structures that have been solved. Lots of peer-reviewed articles published about it. It's universally acknowledged as the best CASE system available out there. So how does it work? Let me show you how it works. So I have here my Windows Explorer window where I have collected the spectra that I want to use. And I'm going to start with a fairly simple example, what actually Ryan showed already. So we have ethylenedione. Okay, we have the spectra for ethylenedione. I'm just imported the proton spectrum without anything done to it, like peak picking or solvent detection or whatever. And I'm going to go ahead and do the peak picking manually. And some people will say, why do you do it manually if you have all these nice automation tools for doing it? Well, the thing is that you are doing now structure elucidation, and okay, in this case, that's an ideal case where we have just compound peaks, but in real life, it's not going to be like that. Sorry to disappoint you. You're going to have impurities. I mean, already here we can see something that's not necessarily correct. So you need to, plus also you may have some peaks that you don't know, are they peaks from the compound or are they something else, or, doesn't matter. So in any case, if you are to use a tool like Structure Elucidator, means that you have spent a lot of time maybe isolating the compound and in the end recording the spectra. So spending a little bit more time to do this is not the worst thing that could happen to you. Now, you may have noticed as I was picking up the peaks on this right side panel here, where we have the auto-generated MCD, molecular connectivity diagram. You see these protons appearing, and it just indicates that, yeah, we have a proton, and we don't know too much more about it at the moment. So we have added our protons. Let's go to add the carbon spectrum. We happen to have a carbon spectrum. So we add the carbon spectrum, and we can go and let's detect the solvent here, the chloroform. Yeah, we can ignore these other notes there. These appeared because I had selected to look for that impurity. And I can use my threshold tool and detect the other carbon peaks. And you see now here we have a few carbons that appeared, and they are all marked as CH question mark. We have their chemical shift at the bottom. We see some of them are black, one is purple, others are blue, and there is one green. So the colors indicate what hybridization these carbons are. And the blue ones are definitely sp3, the black ones are undefined, the CH, the purple one is not SP or whatever, SP2. So yeah, that's what has been done. Now let's proceed to add more spectra. So I'm going to add the HSQC. And the moment I add the HSQC, you will see the okay. So we have now the HSQC added. We have the peaks appearing nicely. And we see these green lines. These are the so-called grid lines. And these grid lines identify the areas where we have had resonances in proton and in carbon. So in reality, a signal can only exist in the intersection of these grid lines. Okay, so I'm going to do an automatic peak picking for this spectrum. And the moment the peaks are added, you see immediately the molecular connectivity diagram changes. And we don't have now isolated carbons and protons. We have them grouped. So we have a CH3, we have a CH2, we have CHs. So things are sort of starting to get in shape. Okay. Then the last spectrum you need to bring in is a correlation spectrum. That would be an HMBC in this case. So the HMBC is added. Let me just make sure that you can see this in the same sense. We have again the grid lines, which indicate where peaks could be. So if we have a peak somewhere outside of the area, then that's not a peak, that's an artifact or whatever. The moment I click this, the peaks are identified, and we see here some arrows appearing. And the arrows now indicate the correlations found. So we see here there is this green arrow correlating this CH3 with this CH. And the fact that it's green means that it's 2 or 3 bonds away. There are some purple arrows. These mean that they are 2 to 4 bonds away. And at this moment, we have sufficient NMR information to attempt solving this. However, we need to add one thing, and that is the molecular formula. So I'm going to go here in our tool to enter the molecular formula. And I can type here the molecular formula. Slight problem, I don't know the molecular formula, but I know the molecular weight. So I can launch my molecular formula generator. And I'm going to say here that I have a molecular weight of 160.1. And yeah, that's not a high-res spectrum, so I have an error of 0.5. And I'm going to select to generate the molecular formula. And we see the software faithfully generated all possible molecular formulas that sum up to 160, including oxygen 10. This is a good first step, but it's not really too helpful because, you know, these things are not just not possible. However, we see here that some of the limits defined for carbons, protons, whatever, are very large, 0 to 100, 0 to 100. That's not the case, though, because we know exactly how many protons we have. We know how many signals we detected. We know how many signals we detected in the carbon. So I can select here to predict the limits. And this really sets things now as they should be. So it says 11 carbons. And if I go now to generate molecular formula, we see that in reality, there is only one molecular formula that matches all the information that we have. So I'm just going to select it and say, okay. So we see now that this oxygen appeared here. And the next step is to check this molecular connectivity diagram and see if it is consistent and reliable and proper. So it tells us that it is an easy solution, an easy problem. And of course, I'm showing it to you now. So the important message here is the first lines here that it passed all tests. So there is no problem with the molecular connectivity diagram. We see some warnings that some carbons do not appear correctly and some protons have not been matched. That's not an issue. I can click OK. And then I can go on the generate. And again, I'm told that the problem is easy. And now here I have all sorts of options for the elucidation. I'm not going to go through each and every one of them. I'm only going to indicate here the options for enumerate possible valences for nitrogen, sulfur, and phosphorus atoms, if you have different such things. Also, allow bonds between heteroatoms and allow bonds between heteroatoms of the same type. If you believe that you have something like that, then you should tick it. Now, in this case, with just a single heteroatom, doesn't make too much sense. And then we have the option for fuzzy generation, and fuzzy generation has to do with elongating some of the bonds in order to try to find some structure. In case you have many correlations with 2 to 3 bonds, you may be over constricting the problem and you may have had some non-standard correlations, that is longer ones. So yeah, allowing fuzzy generation can help there. Finally, we have the filter options. So yeah, it doesn't allow you, for example, to generate a 3-membered ring with a triple bond. I don't believe any such thing exists. But yeah, then everything is checked with in terms of the chemical shifts, and yeah, things are done. So I'm going to click OK, and we see it starts generating, and after very little bit, it should show the result. There you go, something's happening. It normally finishes within a few seconds. It took a few more seconds now, I guess that's thanks to Zoom and screen sharing and everything. So we see that it generated quite a few structures. And if you have been paying attention, you may have seen that some of the structures are similar. They're similar chemically, but if you look at the numbering, for example, it's not the same. You see here it goes 10, 9, 5, 7. Here it goes 10, 9, 6, 7. So the numbers are chemically, the structures are chemically equivalent, but they are not mathematically equivalent. And the situation here is that the software will take everything and solve the problem from a mathematical point of view. So mathematically, yeah, these two structures are not equivalent. Chemically, they are. So in order to put a bit more sense here, I'm going to go to this other interface where I have all these structures, and I'm going to select here Tools, Remove Duplicated Structures. And after a few seconds, I am told that, there are only 6 structures left. So which one is the correct? Well, I'm going to go to Sort and say do the sorting automatically. And after a little bit, I'm told that this is the best structure, and you see it's all highlighted in green. And the others are not that good. And then we have some more metrics generated. So we have this DN, which is the mean deviation between predicted and experimental chemical shifts for proton and carbon. And we see that this is extremely low, 1.7. For the next structure, it's 4.6. We generally want this number to be below 5 in order to deem the structure correct. So it needs to be below 5, and it needs to be far away from the next one, at least 1 ppm. And yeah, here it's way below 5, and it's almost, 3 ppm different than the next one. So yeah, there is no question this is the correct structure. And then, yeah, also we see the incremental calculation for carbon and whatever. We can calculate several more metrics for that, and proceed with concluding which is the correct structure. And this was just an illustration of how to set up the system and how to calculate things. As I said, we have been running structure elucidations for more than 25 years. And we have, if you go on our website, we have here in our resources, we have the elucidation of the month. And you can see here some examples of structures that have been elucidated, and we are posting the results here. Most of the structures come from the literature. So we are going through the literature and looking structures that have been solved, and take the data, input them, enter them into Structure Elucidator, and see if we get the same structure. And then, yeah, we put it here. So you can see all sorts of structures have been solved: small, big, simple, complex. Look at this monster here, for example. So yeah, there are lots of things that can be done with Structure Elucidator. Let me go back to the software though, and let's put things a little bit more in reality. So this was an example where I showed you how to solve a structure by knowing nothing. This could happen, but this is not necessarily the case. Can be that you know a little bit about the structure. You may know some parts. So how do you handle that? So let me close this, and I'm going to show you another example, more a bigger molecule and more real life. So let's go with this strychnine example. So this is a data set for strychnine. I believe Ryan showed it also. And once it's open, we can see that, the molecular connectivity diagram has been generated. We have the best structure found. This is a data set now that contains proton, carbon, HMBC, and HSQC. And I have already run this. And if I go in view elucidation protocol, I can see here that it took 55 minutes. I'm not going to repeat this run. We don't quite have 55 minutes today. But I'm going to show you two things. So let's say that you have what you are searching for, what you are working with here. Let's say that it's a natural product or something that was isolated, from either a natural product or something that came up, I don't know, in a new production batch that you had. And the spectra could have been familiar. You may have seen them before. So what could you do? So to help with this, we have developed since more than 10 years now a tool that allows you to search for compounds that have been published in the literature. So we do it with this tool here, search chemical shifts. And what we have done is we have taken the contents of PubChem, which is more than 110 million compounds, and using our predictors, we predicted the carbon spectra for all of them and organized them in databases. And we are distributing this together with the software. And what you can do now is when you have your actual data, you can search this database and see what is there that could have a similar spectrum to the one you are observing. So that's what I'm going to do now. I have this data set here, which has the carbon resonances, and I'm going to search this database, and I'm going to say, the only options really to look for is, allow lack of signals and allow excess of signals. And these have to do for the cases when you had signals that were not detected because maybe you didn't have enough and you had low intensity, so you may have missed some quaternaries. And or in the case where you may have had an impurity that somehow went there and you didn't realize it's an impurity. So you don't want this to ruin this search. So these have been left to quite lax 5 and 10. But then we can define the composition and I say, I have the molecular formula. So that's my molecular formula and, do the exact search. So don't go for anything more. And that's it. Then I'm going to click search. And it informed us that it's searching a range of monoisotopic masses. And right now it's going through these 110 million entries and trying to find what is there that would have a similar spectrum. Now, obviously, 110 million entries are quite a few. The size of this database is pretty significant. But we will see in a second what this tool can do. So, I also selected to use the best stereoisomer as well. So here you go. I click OK. It's telling me that it used data from the PubChem as it was in May 2023. We aim to update this database once per year in the spring timeframe. So we will be having a newer one in the next few months. So let me go here and see what structures have been found. And we see that these are the structures that were found in PubChem that have a spectrum, a carbon spectrum similar to what we have recorded. And I can go here on this one, for example. And I see here all the information, including the PubChem ID. So I'm going to select, where is it? Copy item value to clipboard. I'm going to go back to my browser and say PubChem. Just going to paste this number and search and see what is this thing in PubChem. And well, it's strychnine. Okay, so imagine that you have isolated a natural product. This provides an extremely quick means of finding out whether what you have has been found before. If you don't find something exactly the same, then you will get ideas on what it may be. Now, in terms of getting ideas of what it may be, we have another tool that we are offering, and this is the fragment searching. So I can go here and select to search for fragments. And what it's going to do now, it's going to search our database of, I think, 2.5 million possible fragments that could exist in chemical compounds. And yeah, show us what could be in there. So I'm going to select again the same thing. So use from molecular formula, and I'm going to go for fragments between, say, molecular weight of 50 to 150, maybe. And let's say search. So it's going to start here the search. It's finding fragments. And after a few seconds, you will see the results for the fragments. The fragments will also be sorted. So here you go. I'm gonna click close. Oh, I'm gonna click OK. I'm gonna click close. Let's go and see what fragments have been found. Okay, so you can see some things that may remind you of something. And yeah, I can select one of them. I'm not sure which one to select. Tell you what, let's try this one. Okay. And I'm going to right click here and say create molecular connectivity diagram. So and sort them. So I'm going to use this fragment, and it's going to generate possible molecular connectivity diagrams based on that fragment. So it has defined a part of it. And then you can try to solve the structure. Now, this definition was done using the fragments in the database, but you can definitely use your own fragments. And if I click now to generate, let's try with this MCD and see what it will do. Again, the same parameters and clicking OK. Okay, we see it doesn't. Let me stop it. That's probably not a good fragment. Let me try this one. No. So yeah, this can allow you to have the solution much faster. Now, unfortunately, the fragments didn't quite do it. Let me try it once more. Let me search fragments up to 200. So yeah, you normally want to have, the biggest, the largest possible fragments. But let's see. Okay, here we go. And if I go again here, I'm gonna see other things. So let's maybe select this one and say, there you go, generated one. And if I try to solve the structure now using the user MCD, you see it's going to go much faster, and there you go. You already see messages that it generated the structure, the proposed structure. So yeah, you can see the strychnine structure appeared. And this took a few seconds versus the 55 minutes. So adding a fragment can help a lot with structure elucidation. Now, I don't think that we have time to show you more things. I don't know, do we have any questions on this? I mean, there are a few other things that we could show you. We could talk about finding the configuration using either noises or residual dipolar couplings. But we are at the 2-hour mark. Is there a question there? So I see a question, could the structure elucidation work also with polymers? Polymers, I presume, who is asking this? Roberta, yeah. So if you have a polymer, then you don't necessarily want to do structure elucidation, strict structure elucidation, and we saw it here. You may want to do something like a database search. We are offering a database of polymers, and if you have a polymer, you can search this database to see what is there that is similar. It's not, quite common that people would try to match it, each and every resonance of a polymer to find the to solve the structure completely. I don't know if it makes sense. Okay. Okay, thanks a lot, says Roberta. Do you have any other questions? If you have other questions, please feel free to unmute yourselves and ask, or type it in the chat box. And I'll leave it up to Dave to decide
Okay,
when
great.
we conclude.
Well, thank you, Demetrius, and all our speakers. And before we quit, let me turn things over to John. I see he is here. John? Maybe he is not here. Okay, so if there are no more words from John, then let me conclude the meeting and thank everyone again. And we'll see you.
Thanks a lot, Dave, for giving us this opportunity, Dave and the Ivan people. And yeah, see you next time.
Okay.
Thank you,
Sure,
everyone.
come to Asilomar. Oh, John?
Yes.
No, I guess not. Okay.
No,
Hello.
John.
Bye. Okay, bye.
Okay, thanks. Bye. See you at Asilomar. Bye.
Okay.